Professor Mariana Vargas Magaña from Instituto de Física. It's nearby here, so you can go also to there to ask more questions. Maybe so, and she will talk about the cosmological results from DESI. Please, Mariana, thank you for accepting.
Great. Well, sorry because my glasses are telling on, so I will be like that. Thanks everybody, thanks Alejandro for the invitation, and thanks everybody for being here. So today I'm gonna talk about DESI. Maybe you have heard a lot about DESI recently. It's just because in March we released another analysis of 2 years of data. And this analysis is based on the Brownian acoustic oscillation. This is part of what I plan to present today, but I will try to introduce as well another analysis that we did very recently as well, but in November of last year. We released this analysis at the end of November, and we also have a big release, but we didn't have many presentations, at least in Mexico. So I plan to take some minutes to present that work as well. Okay. Well, first I need to thank all the sponsors of DESI, because thanks to them we have the experiment going on. So in the left side we have all the sponsors of DESI that are funding the running of the experiment. And then on the right side we have all the institutions that participate in Mexico, and we also want to highlight this participation, Mexican group. So the outline for today is to start with a very short presentation of what is DESI, and what is the motivation of having DESI, and what is the context of DESI. So I will be talking about many dark energy experiments, because DESI is not the first one, and I want to present all the history of experiments, spectroscopic surveys that are used to investigate dark energy. And the second block is the main goal of the talk today, is to present the results of BAO that are released too, and what are the cosmological consequences of them. But before that, I will require to introduce a lot of stuff of how we extract this information from galaxy surveys. And this is the first block of main important block. Then in the second part, this part I plan to go very quickly, and it's the other work that I also introduced at the beginning. DESI has two observable, Brownian acoustic oscillations and redshift space distortions, and the second analysis is based in what we call redshift space distortion, but in correct language we use more the words full modeling of the two-point statistics. And I will end with what is next, that is going to be very short. So what is DESI? DESI is the acronym of Dark Energy Spectroscopic Instrument. As its name is saying, it's a dark energy experiment. And why we care about dark energy? Well, I think I like to quote this from the report from Osnomas 2022, why dark energy is important. So dark energy is a fundamental open question. And whatever is causing the cosmic acceleration is going to bring us to understand new physics. Either if we find that dark energy is a new component that is beyond the standard cosmological model of particles, the standard particle physics model, or either we find that the gravity is not the best model, and we need also to go beyond general relativity to explain the cosmic acceleration. But in any case, whatever we find, it is going to bring us to have new physics. So that's why I think it's very important. So given the relevance of the questions, there's been a lot of effort, experimental effort to understand this question. So this is a timeline of experiments. Each box is an experiment that took place in the past and that is planned in the future. And we are just here. The orange box is DESI, so DESI is not isolated. It's one of a series of experiments that have been running the last 2 decades. We have here most of them that are here are coming from previous versions that are slowly survey programs, and all devoted with the program devoted to dark energy. So in this timeline, you also see some dotted lines that is indicating different stages. So we have here in the intersection between the stage 3 and the stage 4. So we are in the transition between these two stages. And each stage is telling us what is the progress in the understanding of this open question that we have at this time. So this progress is measured in terms of the figure of merit. The figure of merit is defined in terms of the inverse of the error bars of the equation state of the dark energy. Here is the equation state of the dark energy. Here are the parameterization that we use for the observational surveys analysis, where we have two parameters, and in terms of the errors of these two parameters, we are kind of measuring how we are progressing in the understanding of dark energy. And the best is to decrease the error, so to increase the figure of merit. The larger figure of merit, the best. And we are here in stage 4. At the end of stage 4, we plan to have at least 3 times better constraints that we have to stage 3. So we have in this transition, and that's why it's very important, and there is a lot of people looking at the results of DESI, because it's the first experiment of stage 4 that is providing results about dark energy. So how it looks like this progress in terms of the figure of merit in a figure. So this is a forecast that is in the white paper, and the red is what we plan to obtain with DESI, that is the contours of confidence. And then we have what we had with BOSS, that is a stage 3 experiment, and you can see how we expect to have a shrink of the contours of the parameters of the equation state of dark energy, and that is the main goal of DESI. So DESI as well is a collaborative effort. So we are around 1,000 members around the world, spread in 72 institutions. And these are the names of the people that are participating in Mexico. We have researchers and students, and you can see here that we have many students working on this. And also I like to say that this is not just a collaborative effort, it's a cumulative collaborative effort. So maybe if you work in the past for DESI, you are contributing to the results that I'm going to present today. So what is the instrument of DESI? That is going to be very quickly. So we use a telescope, so it's a 4-meter telescope that is in Arizona, in Kitt Peak Observatory. This is the telescope, it's a Mayan telescope. With this telescope, we use it to install the DESI instrument. I'm not gonna stay in this video because it's very long, but inside this, we have a telescope, and the most important part of the telescope is the focal plane. For the focal plane, we have 10 petals with 500 fiber positioner each that are controlled robotically and automatically. And that is the technology that allows us to pass from an order of magnitude more objects that we have collected in 2 decades with past stage 3 experiments. So you will see the numbers later on, and here you only will see like the simulation of how this looks like, all these robots working together to position the fibers to take the light of the galaxies, and then pass this light to the spectrographs that allow us to get a redshift for each object. So this is more or less the timeline of DESI. So the timeline of the DESI survey data taken. So we started in 2021, and the first data release is about 1 year of data. So this is what we call data release 1. I mentioned because I will use this later. And then we collect 2 years more, and we put together this 1 plus 2, having 3 years of data, and then this is what we call data release 2. So we plan to have in DESI 3 data releases: data release 1, data release 2, 3 years, and data release 3 that is going to be the final survey, 5 years of data. So these are numbers for the different data releases. The number that we have in data release 2 and data release 1 is actually the object that we have in each of the data releases. Data release 3, here I put the numbers of the white paper that are like pessimistic. We know now that we are going to collect more than the numbers that we have here, because we are getting more spectra than expected, because we have a good performance of the instrument. And the one thing that I want to highlight from this slide are that the numbers that we collected from previous surveys of different tracers are one order of magnitude below what we are collecting in total with this. So this is the great challenge of this instrument and the big difference between the stage 3 and the stage 4 experiments. And this difference in the number of objects is what, and the redshift range that we are covering, what allows us to shrink these contours of what I showed earlier. So just here, just to mention, because I'm not going to mention again later, in DESI we have 4 tracers, luminous red galaxies, emission line galaxies, Lyman alpha quasars, and quasars that we use as punctual tracers. So this is more or less the footprint of DESI. So in black we have delimited what is what it's gonna look like the survey completed, and then we have here in colors what is covering data release 1, and then they're gonna appear what is now data release 2. That is the other analysis that I'm presenting today. So for the rest of the talk, the results coming from BAO are coming from data release 2, and the results I'm going to show briefly of full modeling is about data release 4. So you will ask yourselves why these two analyses have different timelines. We will check a little bit later. In general, I think preparing the analysis of full shape took longer because it's a more complex analysis. So in general, all the RSD analysis is going to be released with some kind of delay with respect with BAO papers. That for the methodology is more straightforward. There are not big changes in the methodology, while in the full modeling we have been updating a lot how we are doing the analysis for extracting the cosmological information. So, as I mentioned, what is published, what is released as now is the data release 2 BAO papers that are 3 years of data, and data release 1 full modeling that is the second part. So, for those of you that don't know exactly what looks like a spectroscopic survey, this is a visualization of how it looks. So we have all these points are galaxies that we have the angular positions, and then we put in the DESI instrument to take the spectra, and with the spectra we can infer the redshift, and with the redshift we can have the radial coordinate, and we have this 3-dimensional map of the large-scale structure of the universe that we use to infer cosmological parameters. So how we extract information from these galaxy surveys? So basically, we have this data that are catalogs of galaxies, and with this data we can compute density fields, and with these density fields we can get the fluctuations of these density fields, and for modeling these fluctuations of the density field we use the concept of random field. So for describing a random field, we need to use the moments of probability of distribution, and then we have, these are the moments. The first moment is the mean, the second moment is the 2-point correlation function, and then for describing a random field in general, we require the n moments of this distribution, so we can go on. If we have a Gaussian distribution, Gaussian random field, then only the 2-point correlation function is required for describing this Gaussian random field. In general, all the analyses I'm not going to present today are based on the 2-point statistics, and up to now this is what we are using. For future analysis, for example, for the next data release 2 full modeling, we plan to use higher order statistics as well. Okay, so for people that have not computed yet ever 2-point correlation function, so I'm going to describe very briefly how we can estimate a 2-point correlation function from a catalog of galaxies. So we have these galaxies, and then the estimator that is most naive, but is very clear for explanation, is we're gonna take pairs of galaxies, and we're gonna measure the distance between each pair of galaxies. And we are gonna construct a histogram with this. And we are going to compare this histogram of distance between pair of galaxies with what we get with a catalog that is completely random. And this ratio between two histograms will give us what is called the two-point correlation function that is going to appear here. So this two-point correlation function, if we do it with current galaxies, it's going to have this form. And we're going to check, we're going to observe a feature that is called, this small peak, that is called the baryonic acoustic oscillation peak. And this is going to be the observable that we will use to explore the spatial history of the universe. Okay, so the two-point correlation function that I presented is based on isotopic distribution. There is no source of anisotropy. We know that there are some effects that will affect anisotropically the two-point correlation function. So we used to compute the two-point correlation function separating two distances, two vectors, the part of the distance along the line of sight and the part of the distance parallel to the line of sight. So we have the observer, and this is parallel and perpendicular to the line of sight, and we are going to do the same exercise that we just presented. And then the two-point correlation function with a peak will appear like this. The peak is going to become this ring, and this ring is going to provide all the DL information. So we don't analyze directly the two-dimensional two-point statistics. We project the information using the Legendre polynomials, and then we analyze directly the multiples, monopole, quadrupole, and hexadecapole. And with that, this is what we compute with data, and this is what we compute also with the models to compare both. So, as I mentioned, DESI has two main observables, baryonic acoustic oscillation and redshift space distortion. I'm gonna start now talking about baryonic acoustic oscillations. So, the baryonic acoustic oscillations imprinted a characteristic scale in our universe that, this is an artistic view, but it illustrates what we are trying to measure. So, we have some regions where we have more galaxies, and the distance between two pairs of galaxies, we can find that there is a typical scale where we can find the separation of two galaxies. And this is exactly this scale what we are going to use for exploring the expansion. So how this feature is imprinted in the large-scale structure of the universe, we're going to use this cartoon. So we focus in overdensity. In the early universe, we have the baryons and the radiation are coupled, and then in this plasma, we have two forces that are acting. First, the gravitation wants to collapse, the matter wants to collapse, and then the radiation opposed to this collapse, and it generates an oscillation in Fourier space that, if you introduce in the configuration space, is going to become an overpressure wave that is going to start to propagate from the initial perturbation, and this will continue to propagate until the decoupling time, when the photons don't have enough energy to interact with the baryons, and then stop interacting, and they can travel freely, and the baryons get frozen on this characteristic scale. And this happens at every single overdensity. We have this spherical shell of baryons that move away. And then at the end, this configuration remains in the overdensity of matter in general, and this is where the galaxies form. And we expect to measure this pattern that is imprinted from this early physics in the distribution of galaxies that we measure from this. So how we use this feature? So basically, we can measure this DL feature along the line of sight and across the line of sight, and then these two different measurements will give us information about the Hubble distance and about the angular diameter distance. And we know already that the distance depend on cosmology, as we know. And this is where this is the thing that allows us to traduce this BO feature in cosmological constraints at the end. So we can measure this scale at different effective redshift, this apparent scale, and then we can populate this Hubble diagram with different points that are coming from the measurements of BO. So each tracer and each redshift beam, we can construct this two-point correlation function, and then we can extract the information from the BO, measure the dB parameters, dB, dA, or dBH, that are distance that I just mentioned, and then populate this Hubble diagram. And then from here, we are gonna produce the inference of the cosmological parameters. So what we measure BO at the end is dH over RD and angular diameter distance over RD. RD is the sun horizon. That is the distance that travels this sun wave between the end of the inflation until the decoupling of the baryons. And we can compute it from this equation. Okay, so I'm not going through the detail of how we do this in real life. It's just like a very schematic slide. So we have a template with a fixed cosmology, and we modulate all the variations around this fixed cosmology with these parameters alpha bar and alpha pair that depend on late time variables. So are related with the distance. So we are kind of dilating the coordinates along the line of sight and across the line of sight, and this is for mimicking changes of the cosmology. And when we fit these two parameters, we are at the end getting constraints on the M and the H directly. So this is what we produce, the BO measurements. So what we are gonna see here in the next point is the BO measurements that are taken in the cosmology paper for doing the inference of cosmological parameters. So we can now have all the elements to understand the cosmological constraints. So again, remind you that this is over data on these two samples, 3 years of data. That is the second that is going to be here. With this data with these two, we have all these tracers, and we can estimate the two-point statistics. And with this two-point statistics, we are gonna use BO methodology for extracting the dB parameters. All these papers related with this work are here. So the 3 first papers are named key papers, and I'm gonna center in the third one, that is the one that describes all the methodology for inferring cosmological constraints from this dB, dH, and dA that I just presented before. And all these papers are the supporting papers where all the methodology is described in very, very much detail. So if you are interested, I really encourage you to look at all these papers. So I'm not going through all the details of the analysis, but I just want to say you that it's not trivial. So there are many steps that I'm skipping just because I just want you to have the idea of what we do. But I'm gonna highlight a few things. So in this analysis, it's the first time that I applied something that we call blinding. Blinding is for hidden the data. We kind of introduce some modifications in the data, such as we can analyze it without knowing what is the cosmology that is telling us this data, right? And we do that to avoid bias, personal bias, so confirmation bias is called. All the methodology of this blinding is described in these papers. We also have a lot of work done for looking for systematics. So as we are going to infer cosmological parameters from this data, we want to make sure that all these measurements are robust against different changes in the methodology. So we look at different BO modeling potential systematics, imaging systematics, different choices that we do for the analysis. And what you are looking in these different columns of each different tracer, we perform this test. We apply the methodology with these variations, and we check what is the variation of this parameter with respect to the baseline choice that we decide. All this is also in this paper of validation of the DESI DR2 measurements. We do the same with Lima alpha. That is another important part of the analysis. And we have 3 papers related with the Lima alpha analysis. So at the end of the day, we have these measurements. These points are the dm over dh, and then we have all the different colors and different tracers, and the different light versus purple, solid purple. But solid versus light indicates what we get in previous data release 1, how it compares with data release 2. These are the measurements. That it looks like this in these diagrams that I presented. And then I'm going to start with the cosmological constraints. So the first thing that we check when we perform this analysis is the consistency between the DESI data. And one way to do that is to check, to take each tracer and to perform the inference of cosmological parameters, and then do the same for another tracer, not combine them, and then infer the cosmological parameters. And what we want to check is that all different tracers are pointing to the same region of the parameter space. So this is what we are looking at here. So QSO, PES, LRG, LRG2 are different contours, are coming from analyzing just one tracer at a time. And then at the end, we're going to add the final contours that are when analyzing all the tracers together. That this is really what we use. The previous exercise is just to check the robustness of the results. And what we see is that all the tracers point to the same region of the parameter space. And second, we have here the result, but we have all combined all the tracers. These are the constraints. 2 things to nothing. For nothing, the first one is that we have a 40% improvement of these parameters with respect to what we have the previous data release. And the second, and this just noticed here, I obviously introduced that before, but I tell you again, VAO alone only give information of the product H0 early. We cannot get information alone with only DESI about H0. So we will see later what need to add to add a constraint of H0. A second thing that we want to use for checking about the robustness is to check if our results of DESI today are consistent with previous stage 3 experiments have gotten in the past. So in brown, we have the results from a stage 3 experiment, as long empirical survey, 2 decades of data that was analyzed here. How it compares with the dotted lines are what we got in data release 1, and the blue contours are what we got with data release 2. So again, 2 things to notice is that Sloan and DESI are completely consistent, and then DESI data release 2 and DESI data release 1 are completely consistent as well. So all these things just are showing how robust is the DESI analysis up to what I have shown up to now. Okay, so now we haven't really combined yet DESI with anything. So we are going to start checking how it behaves compared with other observables. So here in pink we have the CMB, in blue again we have DESI, dotted lines, and DESI data release 1. And one of the things, of the highlights of the paper, of the construction of the speech of the paper, the history that we want to tell you, is that compared with data release 1, the tension, the discrepancy between VAO and CMB increased a little bit. And that's why, the reason for that is because the contours of the DESI data release 2 shrink a little bit, and then the discrepancy with CMB increases because they are not exactly in the same part of the parameter space in these 2 parameters. So I'm not going to say more here. I'm going to continue constructing the history of the paper, or the basic history that we want to tell. So having a 2 point something discrepancy is not bad, so we can combine that somehow, and we start combining here DESI with other observables. I was telling you before that DESI alone cannot constrain H0. We need to break the degeneracy of with adding more information for the RD parameter. And in particular, we can do it in several ways. One of the ways that is the preferred one is one that is independent of the CMB. So we use BBM prior. This BBM prior gives us information about the variance, and this allows us to have information about RD, and then we can constrain indefinitely H0 without any CMB information. And this is what we have here. DESI plus BBM, how it compares with CMB. And then, if we don't want to use all the CMB information, or just part of the information, we can also use the best variable that is constrained by CMB is the theta star. So we can compare it on a prior or theta star, and then use only partial information on CMB and constrain H0 as well. So this is the constraint that we get in this combination. So what it tells us about, well, the first thing is that what this tells us about the Hubble tension. So this is the only plot that I have about this. This is the measurement of DESI plus BBM, that is like our baseline analysis for this. And then we compare with choose, that is another observable that is measuring H0 with supernovas. And then we have here that the tension between the two are 0.45 sigma. Okay, now we continue. I think this is the last plot in the context of lambda CDR model. In this plot, we are showing the different observables, again, without combining, and just checking what is the preferred value on the omega m that the different observables prefer. So we have in blue, that's DESI data release 2. In dotted, that's DESI data release 1. They prefer lower omega m value. Then we have omega, the intermediate value of omega m is preferred by CMB. And then the supernova, all three sets prefer a high value on omega m. And again, this plot is kind of constructing this, like the conclusion that I'm going to give at the end, that we start to see with data release dust that is popping some kind of small tensions with the model of lambda CDM. And we start to think that if lambda CDM is really the best description that we have of the universe today. So now we are going to open a little bit more the space, the parameter space. So instead of just fixing to a cosmological constant, we are going to allow the two parameters of the equation state of dark energy to move freely. So we have here what DESI tells us alone about the dynamical dark energy. So DESI alone cannot constrain pretty well the parameters of the equation state of dark energy. That we know is expected. So the best constraint that we get of dark energy in general ever has been done with combining different observables. So we are going to construct this piece by piece. But I want to highlight this. DESI alone is not constraining dark energy parameters pretty well. So we need to start combining with more things. Here is how it compares first data release 1 and data release 2. Again, we see that a consistent picture. But data releases pointed to the same region, and data release does shrink a little bit the contours, as we see here. Then we start combining with other observables. So DESI plus CMB, this is how it looks like the data release 1, and how it looks like the data release 2. So we see that with the shrink of the contours and the shift a little bit the ellipse over this sector, or the values for the equation state of the parameter space. So we start to see that there is an increase of the tension with respect to the lambda CDM model that is here, just in the origin, and the tension is about 3.1 sigma. for data release 2. Okay, next. Now we are gonna combine this with supernova dataset. So DESI plus CMB plus supernova, that is the most constraining thing that we can have. And then we have 3 different sets of supernovae, pattern plus, that give us a 2.8 sigma tension with lambda CDM. And then we have union 3, that is a 3.8 sigma with lambda CDM. And then the DES GR5, that is a 4.2 sigma with lambda CDM. So again, one thing to highlight here is that we confirm what we have observed in data release 1. So here for remind you, in data release 1, we already have observed this preference for this sector in the parameters of the equation of state. We were kind of surprised. This time we already know that we are gonna probably get something similar, and then the result of data release 2 just confirmed this preference of the data for this region of the parameter space. So now that we have this result, so we want to check how robust this result is, because it's an important result. So the first thing that we do is to try to play around with different data sets and to try to understand if there is any fluctuation of robustness. What we want to check is that if we combine any kind of different observables, we get the same answer. This is more or less what we want. And then we start with the CMB, and we compare CMB complete with CMB compressed information. In this compressed information, it's less affected by the issues that we can think CMB has with a lens. So this is one of the things that we wanted to explore, if this combination was robust against different ways of analyzing CMB, and we see that it is. When we can also do a kind of test with supernovae, so there will be a bunch of papers saying that the supernovae at small redshift have some issues. So we want to check if this is the source of this preference. So we here are comparing how DES, combining with DES, eliminating this low redshift supernovae, how it compares with using all the supernovae, and we see that the preference of all these regions remains as well. And then we can also say, well, okay, we don't believe in CMB, we don't believe in supernovae, but we are going to use another observable, and we use DES GR3 lensing, the 3.2, and then we also combine with the supernova. And then we also see the preference for this region. Okay, so all these tests tell us that this really conclusion that is not really coming from one side. So we have different directions that are telling us this preference for this region in the parameter space. I'm gonna skip this. Okay, so I'm gonna pass for the last part of the cosmological constraint for data release 2. So DESI alone cannot constrain massive neutrinos with BL only. It can do with full modeling, but not with BL. With BL only, that is the purpose of this first part of the talk, what we do is, we know that CMB constrains the mass of neutrinos, but it's kind of degenerated. So to probe this degeneration, we use the DESI information that tells us information very precise about omega m, for example. And then combining these two observables, we can get constraints on the sum of the mass of neutrinos. And we can have this constraint from this combination that is really what we presented for a lambda CDM model. This is the value. This is the posterior, the one-dimensional posterior, that is 20% more precise than we had in previous data release. But one of the things that is also highlighted in the paper is that this is very close to this is an upper limit. It's very close to the lower limit that is coming from neutrino oscillation. So this is also some of the things that are kind of looking interesting, let's say. Okay, so in the context of all what I have presented before, we can ask ourselves, well, if we analyze the sum of neutrino masses in the context of a model that has more degrees of liberty, and we allow as well to move the dark energy parameters, and then we have this constraint that is here. Obviously, the posteriors gets larger, and we kind of see as well that the posterior is more centered in positive values as well because of some of the mass. So this is the result with DESI in the context of this extended model. There is a full paper about neutrino physics that I recommend you as well to read, where there are a lot of extensions. Between different extensions are different ways of analyzing this data that are shown here. Yeah. So the conclusions are of this analysis is since data release 1, we already have seen this kind of choking. Well, we kind of see this preference for a dynamical dark energy as the best solution for cosmological model. With data release 2, we have seen that this evidence is more clear. So the language of the paper is charting the evidence. And the tension with lambda city model can come between 2 point something to 4 point something. That is a very strong statement. In any case, one of the things that is clear with this data release 2 analysis is that are popping more kind of tensions with different data sets, between different data sets that I pointed out in my presentation. And we can say this like lambda CDM is being challenged by these different tensions that are emerging. Well, probably we are seeing a really a proof of a big change that is going to be changing from a dynamical dark energy paradigm instead of a lambda CDM paradigm. So I have 5 minutes. I have 5 minutes, so you are not going to hear anything about redshift space distortions, I think. Well, I'm gonna give you just the idea, and then I'm gonna go to here. So the other observable I didn't talk about is the redshift space distortion. So it's an observational effect. So if you remember, we measure redshifts, and with this redshift we infer distance. But these redshifts are contaminated with peculiar velocities. We have a part that is coming from the Hubble flu and a part that is coming from the peculiar velocities. That means that if we have the observer here and these points are real galaxies and these arrows are velocities, what we should measure is these real space positions, but what we measure in redshift space is this. So all these positions are collapsed because these particles are following an overdensity and they are going through the overdensity, and in the redshift space we see it as distorted as it is here. So this distortion generates that the isotropic two-point correlation function that we should have is distorted as this, and then analyzing this anisotropic two-point correlation function, we can extract information, extra information that we cannot get without redshift space distortions. And this information is coming from the velocity field. So this velocity field will give us information about the growth of a structure. So analyzing redshift space distortion allows to constrain the growth rate of the structure. We are accessing to how the structure grows and getting information from there. So in a similar way that we have the Hubble diagram, we have F sigma 8 diagrams as a function of the redshift, and with different with different catalogs, we can measure this using the two-point statistics full modeling, and then extract conclusion from the here about the cosmological parameters. And in particular, also it's interesting that with this redshift space disclosure, we can have access to testing the general relativity. So this is just for illustration. We have how these two different lines depend on the gravity model that we use. And so it's clearly how we can use this observable for testing as well general relativity. And we'll keep this. So there are several ways for analyzing this that I'm gonna skip. But the information is coming from the full shape of the clustering, and we use that to constrain cosmological parameters. So, 2 minutes? Okay. So, again, the source of all the analysis is the two-point statistics. Instead of analyzing the BAO position, we are going to analyze the full amplitude of the two-point statistics. The modeling is more tricky, so there are many papers about the modeling and the methodology for extracting the cosmology. And then we choose one of these ways of analyzing. These are the papers related with the analysis. And then the constraints that we get, additionally what we have in the past with BAO, is that now we have information about the sigma, the amplitude of fluctuations. And then we can do a similar exercise that we did the agreement between different tracers, how different tracers tell us about this growth of the structure and omega n, and we can see all of them are in agreement. And then we can check here in this slide the complementarity between BAO and full modeling. So full modeling is feeding with information about the expansion disorder of the universe, and then full modeling is feeding with this growth of the structure information, and altogether can give us these constraints that are in black when we combine the two observables. So one of the things that we test in the context of the growth of the structure is we can